Hello everybody, myself Rajiv Singh Narana Physics faculty. So in the last video we have finished concept of area vector. So right now we are here to discuss concept of electric flux, right? Okay. So first of all we will see the definition, then its mathematical expression, then its formula, significance, and all these things we can proceed one by one. So see, definition is what? I have tried to write in your words and simple way. The number of field lines passing through perpendicular area of cross section is called electric flux. You have to understand this one. See, number of electric field lines passing through perpendicular area of cross section is called electric flux. Okay, it is represented by phi A. So see, this is the very important mathematical expression. Number of field lines passing through perpendicular area of cross section. This is the definition. But thing is that when you are going to solve the numerical, it's not necessary they will give you area according to you. They can give area of any shape, any size, any direction, so that we can taking here any random shape area, right? Okay, such kind of area you can take any kind of area vector, any kind of geometry. I take this kind of geometry, and suppose that in this space there is a uniform electric field E. Okay, so uniform electric field E. Now here we have to calculate electric flux. So you can see this is not a uniform geometry. This is a random or variable non-uniform geometry. So for this sake of convenience or for procedure, we will take a small area. Suppose this I take this small area, right? And we know that every plane, every surface has area vector. So this area vector will be in this direction. Suppose that dA, what? dA, or you can say ds. Getting my point? Why dA? Because I select this one very small, so area vector will be also very small, and this is a electric field E. Suppose that this angle is theta. It means here theta is what? Angle between electric field and area vector. Okay, can I take this part here? Yeah, I can take. So just going to make the zoom form. Zoom form means large size. See, I select this is a area ds. This is a area ds. Okay. Okay, this is our ds. Okay, and this is a electric field E. This is a theta. So we cannot say this is a perpendicular to electric field, because we know that this plane is at some angle. So I have to resolve to this area is a area vector ds, and area is a vector quantity. This is a ds, na, direction of ds, and area is a vector quantity. So we can resolve into two parts. In this direction, this will be ds cos theta, and in this direction this will be ds sin theta. Again I'm telling you, once you will get this knowledge, once you will learn this concept, then never ever you will feel or face any kind of problem in electric flux. So please be attentive. If you did not, if you not getting anything, so please message me right now. See here, I have resolved this one in two parts. So can I say here two plane, because we know that every area vector is perpendicular to plane. So this is this vector, right? It means its plane will be like that. See this vector, so its plane become like that. Okay, this is a plane and this is a area vector. Why? Because area vector always perpendicular to plane. So this become ds cos theta. Okay, see another area vector is here like that. So its plane will be like this. Why? You can say because we know that area vector is perpendicular to plane. this is a ds sine theta. And my dear students, here is a electric field. Now you can say which area is perpendicular to electric field. So definitely you can say this area, this red colored area is perpendicular to electric field. It means this one will give electric flux, this one will give some electric flux d phi e, which is not equal to 0, but this one will give electric flux which is equal to 0, because this is not perpendicular, this is parallel to electric field. You can see now here, see, this is a electric field and this is a plane surface which is parallel to electric field, so this will not give any kind of electric flux. But this one and this one perpendicular to each other, so they will give electric flux. One simple way you can take another example. Suppose river is flowing, a river is flowing in this direction. So how can you block this river? Like this one? No, you cannot block like this one, but definitely like in this form, if you put your hand like that, then you can block the water of river. But if you putting your hand like that, in this case you cannot block the river, right, or water of river. So this will give flux, but this will not give flux, right? Okay, so from here can I write here d phi, a small electric flux will be uniform electric field, we know, and uniform electric field into ds cos theta. This is a small electric flux. Now we need whole electric flux. So what we can do, we can integrate for its throughout the surface area. So this become E ds cos theta, right? Or you can say E dA cos theta. Getting my points? So this is a formula of electric flux. One more thing, we know that this is a vector quantity and this is also vector quantity. So we can say A dot B is equal to what? AB cos theta. It means AB cos theta is equal to A dot B. Similarly, because both are vector quantity, so both are vector quantity, so we can say this is also phi E is equal to E dot ds. Suppose that electric field is uniform, so this will take outside, so this will become E and this will be ds integration will be S. So finally I am writing here phi E, electric flux become here E dot ds or E ds cos theta or E dot s. This is a formula of electric flux, right? This is a formula of electric flux. This is a general formula of electric flux. Getting my points? Is there any issue? No issue. Now see properties of electric flux. Okay, so see properties of electric flux, right? So first of all, we have got it, the formula of electric flux. You can see from here phi E is equal to E dot S, and we know that dot product is what? A scalar quantity. So we can say it is a scalar quantity. It means what? Electric flux is a scalar quantity. Second property, it's SI unit. SI unit. So you can see now SI unit, electric field Newton or Newton by Coulomb, or you can say volt by meter into meter square. So this become Newton meter square by Coulomb, or another way volt by meter into meter square. So this is volt into meter. So this is the SI unit of electric flux. Third point, we know that phi E is equal to ES cos theta. It means electric flux depend on electric field area of cross section as well as orientation between them. So we can write it is also depend orientation between electric field and S. Suppose that let theta is 90 degree. When theta 90, so phi will be 0. Phi will be 0. So theta 90, it means electric field and area vector. Not I'm telling you area of cross section. Area vector should be perpendicular like that. This is a cross section, so its area vector will be in this direction. So right now angle is 90. So here they will be 0. Suppose that theta is 0 degree. In this case, electric field will maximum. This will be ES. Right? This will be maximum. Just see like this. This is a electric field. Okay. And this is a area of cross section. So this is a cross section. So its area of cross section will be in this direction because area of vector will be perpendicular S. So both are in same direction. So electric field will maximum. Another check, let theta is equal to 180 degree. When theta is equal to 180 degree, in the same case, suppose that this is a cross section and its area vector in this direction. This is electric field, so both are in opposite direction. So here also field will be minus EA, or you can say minus ES. Getting my points? So electric flux not only depend on electric field and area vector, it also depend on orientation between them. Sometimes may be 0, sometimes may be maximum, sometimes may be negative. Getting my points? See the next point. Suppose that we have one cross section here, some field lines coming and some going, and I am not confirmed the incoming lines exactly equal to outgoing lines. Then in this case, incoming lines taken as negative and outgoing lines taken as positive. So this is taken as negative and this they will taken as positive. So net flux will be phi 2 minus phi 1. Getting my point? Net flux will be phi 2 minus phi 1. One more important point, electric flux basically represent number of field lines, and number of field lines represent field strength. Suppose that somewhere flux is present, it means field will be there. So can I write here electric flux represent electric field. More flux means more strength of electric field there, right? So these all are properties of electric flux. Now we will see in the next video problem based on electric flux.